Hello students, welcome to Prushisar's classes again. Today I am going to discuss some basics in fluids, especially liquid. The basic concept in a liquid will be the pressure. Pressure, as you must have known or read in your books, is not a vector. Even though we many times represent pressure as some arrow mark, you must be wondering why pressure is not a vector. It is acting on a surface in particular direction. No, that is wrong understand. Pressure has no direction. We'll proceed now to discuss in details. Let's first discuss what a fluid is, especially what a liquid is. We talk about an ideal fluid or ideal liquid. Fluid is something which flows. Flow means what? Change of shape. Change of shape is known as flow. Okay, if something is flowing, it is a fluid. We restrict ourselves to the liquid. In an ideal liquid, if you imagine any surface in its bulk like this, the force acting on this liquid, force acting on this imaginary inclined surface will be normal only. Normal force, normal to the surface. No tangential component is acceptable in an ideal liquid. Even not an ideal liquid also, if it is at rest in a container, even then also there won't be any tangential component on this surface. So, and this force, which is normal, we could write it as Fn. And this is your area A. Okay. Okay. Now, I'll discuss why there won't be any tangential force. This is the basic definition of ideal liquid. A liquid neither can exert nor can withstand or nor it can resist any shear force or any tangential force on any imaginary surface. If it exerts shear force or tangential force is not an ideal. Simple as it's a very fundamental problem. Okay? Am I clear? That's why if we break open a container, the liquid will simply flow out in all directions because any imaginary surface, there won't be any resisting tangential force to stop its flow. So as I told you, on this surface, there are only normal force, and that force is compressive in nature. It's not a pull force, it's a pushing force on both sides of the surface. Remember this. This fluid force will be always compressive force on a touching surface. Okay, it will not pull it, it will push the surface from both sides. These two things you remember, keep in your mind. I've done a bigger diagram. This is a container and we have got some liquid in it. This is in equilibrium, this liquid is at rest. And I have imagined a prismatic or a wedge-shaped liquid element here. So since the whole liquid is in rest, then so also this prismatic element of the liquid in equilibrium. What are the forces on this? Let's say this is my x-axis, my y-axis, my z-axis. A total 5 forces, one slant, one horizontal, one vertical, and 2 vertical other faces perpendicular to z axis, which I am not discussing right now. And the liquid in equilibrium means net force in x, y, z, both all the three directions should be 0. So this area, vertical area is A1, horizontal base area is A2, and slant area is F3, and the slant area making an angle theta with the base. Are you observing this? And the height of this prismatic element, this height is h. So what is the volume of the prism, right? Quickly come out with answer. It's a basic geometrical question, high school level. What the volume of this prism? Base area into height. If I multiply, I get a cubical shape volume. So it is half of that. So half A2 into H is the volume. What is the mass? Into density. Rho is the density of this liquid, which is at equilibrium or rest. Am I clear? Now let us go for the force balance. In x direction, F1 to the positive x direction, F3 one component will be in negative x direction. Only it is two forces. What I should write? F1 should be F3 sine theta. You see the theta angle. This is theta angle. This is the theta angle here. So F3 cos theta will be vertical. Sine theta will be horizontal to the left. Okay? Nice. Similarly, F2, vertical force balance, y direction force balance, mg downward, F2 upward, and F3 cos theta downward. So very simple, we write it. The upward force must be balanced by net downward force. Upward force is F2, net downward force is mg plus F3 cos theta. F3 cos theta, mg is half rho A2h into g. Okay, very good. This two equilibrium condition we have wrote. Now come to the geometry. Again, I'm showing the diagram. This vertical area A1 is the sine component of the slant area A3. As you can see this, A3 sine theta will be A1. Similarly, A2 will be A3 cos theta. A3 cos theta will be A2. It's a very simple observation in geometry. I wrote it especially. I wrote it very specifically. A1 is A3 sine theta. A2 is A3 cos theta. Again, for your benefit, I'm showing the diagram again. Tell him better, A3 is the slant area. A1 is the vertical area. A2 is the base area. So A3 sine theta will be A1. A3 cos theta will be A2 because this is a prismatic shape. Okay? Means A3's projection onto this vertical face will be A1. A3's projection onto the horizontal surface will be A2. So that's what. Okay, now I am going to do something to see. I divide equation A1 by equation A3. F1 by A1 is F3 by A3 sin theta cancels. Similarly, divide equation 2 by equation 4. What I get? F2 by A2 is F3 by A3 cos theta cancel, and this part divided by A3 cos theta is same as A2. So A2 cancels, half rho Hg. I wrote also very clearly because A3 cos theta is A2. So F2 by A2 is F3 by A3 plus half rho Hg. So F1 by A1 is in the F3 by A3, but F2 by A2 is F3 by A3 plus something else, non-zero. So F1 by A1 is not equal to F2 by A2. You must be observing it, and very true also. But now I am going to reduce the size of this liquid. This size दो बार मैंने लिख दिया. Reducing the size of this liquid element. Okay. While retaining the shape, same prismatic shape I retain, but go on reducing the size means A1 becomes 10 tends to 0, A2 tends to 0, this A3 tends to 0. Just you reduce this size, keeping the shape unchanged. Theta will not change, but H will tend to 0. All the linear dimensions will approach 0. Means the element will be known as a point element. Both all these vertical, horizontal, and slant areas will be maintained, but there will be very small size. And now it is in centimeter square. That time maybe it is will be micron square or nanometer square. Am I clear? Or less than that. I go on reducing to tending to 0. In that case, just see the equation 6. This is the ratios, but this term, rho is finite, g is finite, but h tends to 0. So this term tends to 0. Then what I can say in that case, if we under this condition, when A1, A2, A3 tend to 0, H tends to 0, then half rho Hg tends to 0, then I can combine F equation 5 and equation 6 as F1 by A1 is F3 by A3 is F2 by A2. So only when A1, A2, A3 tend to 0 and H tends to 0, then I can say F1 by A1, F3 by A3, F is equal to F2 by A2. These are three, all these three ratios are equal. This element almost reduced to a point element. Yes, we call this type of element a point element. All areas are point areas. The volume is a point volume. All forces F1, F2, F3 are normal forces on those respective areas. Am I clear? So we observe that at a point, whatever infinitesimally small area we imagine, this Fn by A ratio is unique, irrespective of the orientation of the area. Do you see? This is vertical area, this is slant area, this is horizontal area. But the Fn by A ratio is a constant, as a unique at any point. Understood this? So this Fn by A ratio, when A tends to 0, is unique value at any point. This is known as pressure at that point. This is defined as the pressure. So the Fn by A ratio is independent of the orientation of the area. Whether it's a vertical area, slant area, or a horizontal area, the Fn by A ratio is same. So this is that for a point, this ratio is a unique value. So we call this pressure at that. So since this pressure or limit of Fn by A tends to 0 has no directional connotation because it doesn't depend upon orientation of that area. So pressure has no directional attribute. Understood this? So the normal force by area ratio, provided area tends to 0, then only the ratio will be unique at a point. Doesn't matter whether the area is vertical, horizontal, or slant. Okay? So this is extremely important. So the force exerted by pressure at a point on an area, a small area dA, is a vector because they're normal to that area. Force is vector. So the arrow mark which we saw, that is the force due to pressure. So we, in a homogeneous isotropic liquid, pressure can be treated as a scalar only. Am I clear? So this is what I discussed today, a small conceptual point. Why pressure is a scalar? Because pressure at a point is only defined. You can say it is a point function, not a volume function or area function. A point pressure at a point has nothing to do with what area we imagine at that point. Suppose somebody asks you, find the pressure at this point, Since I've already told you, whatever area I imagine, the pressure is same. But to calculate the pressure here, I should take an area which is convenient to calculate the force. So I'll take a horizontal area, calculate the force by taking the weight of this liquid column on it, divide by that area, that will give me normal force per unit area. And area, then next step will tend area to 0. So that will give a value of rho hg. Then if I say, somebody, you may argue, why I should not take a vertical area at that point? You can take, absolutely, already I given you the license. Any area you take, F by Fn by area ratio will be same at that point. But if you take the vertical area or any slant area, बाबू the normal force calculation भी आप ही के ऊपर डिपेंड करेगा. माने you are right to choose any area, but your responsibility to calculate the vertical or the normal force also. तो चॉइस आपका है. मैं हॉरिजॉन्टल एरिया ले लूंगा क्योंकि आई कैन टेक एनी एरिया. लाइसेंस मिल गया भाई, कोई कौन सा एरिया लूंगा, वर्टिकल लूंगा, हॉरिजॉन्टल लूंगा, स्लांट लूंगा, जो भी लूंगा एफ एन बाई रेशियो यूनिक रहेगा. तो लेकिन मेरा ड्यूटी अभी है कि भाई एफ एन तो निकालना. तो अगर मैं वर्टिकल एरिया लूंगा तो एफ एन कैसे निकालूं? मैं हॉरिजॉन्टल एरिया लूंगा तो मैं वेट ऑफ द लिक्विड प्लस द एटमॉस्फेरिक फोर्स दोनों मिला के ये फोर्स होगा. तो बैलेंस दोनों मिल के नीचे से जो नॉर्मल फोर्स है उसको बैलेंस करेगी. So Fn by Fn will be the weight of the liquid plus pressure force plus the atmospheric force, then divided by area. Then next step is tend area to 0. That must be done. That will give you, the ratio will give you the pressure, and that will come out to be rho hg. That means if this is h, this is rho. Rho a h g plus ये FA, atmospheric air, let's say call it FA, divided by A, limit A tends to 0 is the pressure at that point. So that will be rho hg. A cancel, so no point taking area for this term. There is no area, 10 to 0 has no meaning. But next is Fn by A, F atmospheric by A, limit area tends to 0. This is atmospheric pressure. So rho hg plus P atmospheric. So this is the pressure at this point. Very simple. Suppose I would have taken a vertical area. What should have been the Fn by A ratio? This one. Already the proof is known to you. This one. Provided area this under when A1 is 10 to 0. Then this is the proof. Okay? Now you clear? Did you enjoy this lecture? At least a very basic concept for you, but very important concept for you. Because based on this, we are going to build up the whole fluid statics. So thank you for today. Very soon I'm going to meet you again. All the best to you. Thank you.